Okay, guys, it's time for some fun with math. And so today we are going to finish up the lecture we started last time here. So we have absolute convergence and the ratio and roots test, basically part two. And so just remember last time we talked about this thing called absolute convergence. And so remember, absolute convergence is absolute. So if something converges absolutely, we can conclude that it also converges. And so to test if something converges absolutely, we just look at the sum of the absolute value of the terms. If it converges, then we say that converges absolutely. Basically, we say this series here converges absolutely, and that automatically implies convergence. And then we use the ratio test, which is actually a test for absolute convergence here. So you guys saw that one. And then today, we're going to talk about another test called the root test. And so these are nicely named because, why is it called the ratio test? Because you look at the ratio of the terms. And then why do you call it the root test? Because you look at the nth root of the nth term, or a root of the terms. And so we didn't talk about why the ratio test was true last time. So I want to talk a little bit about that. So focusing here on the ratio test, we want to see, why does it work? So we're just going to fill in some blanks here. So suppose we have this series and we know that it converges. Ooh, I think there's a typo here, so I'm going to have to fix that. So that is not what I want. Suppose we have a series. Suppose, because we can keep suppose there. Suppose sum n equals 1 to infinity of epsilon 5 an is a series. And we have this limit as n going to infinity of this sort of ratio of the two terms is equal to r. So what does this mean? All right, so basically we just have a series. We're taking the ratio of the two terms, the nth plus one term to the nth term. So what does that basically mean? So it means that as n gets bigger and bigger, this ratio here is basically just equal to r. So I'm going to prove this, what we might call it a heuristic proof, which is kind of like a proof that can be used to understand something, but it's not rigorous. So there are small details we're leading out. And so what this means, and I put this in quotes because, it's not perfect because it's a limit. And I did drop off the absolute value. Absolute value just, it makes it more detailed. And I don't want to get into the dirty details. What I want to see is the big picture. And I know if I show you the big picture, you can get in there if you want and get your hands kind of dirty to figure this out. So it means basically, so it's in quotes here, that ratio is actually almost basically equal to r for really big values of k. So I use k here, so a sub k plus 1 divided by a sub k. It's just going to be equal to r for really big, and I said like a billion or bigger, so just really big values of k. It could even be bigger than a billion. It could be a zillion or something like that. And so what does this mean? This means the k plus 1 term is actually equal to r times a sub k. And again, I put that in quotes because it's not exact, but for all practical purposes for us, we could say it's just equal to. And that just comes right from here by multiplying both sides by a sub k. And so what can we now say about our sum? So here's our sum here. Let's just write it out. So I wrote out the first three terms plus dot, dot, dot. I picked it up here at the kth term. And so you have the kth term, the k plus 1, the k plus 2 terms plus dot, dot, dot. And let's get rid of that equals. It doesn't need to be there. And so what is that equal to? And so it's equal to, well, remember, let's do a little math magic here. So remember what a sub k plus 1 is actually equal to. It's actually equal to r k. So what we can do is replace this with r a sub k. And we can actually replace this guy with, because this is true up here, this is actually true for all k bigger than that big value. So it's also true that a sub k plus 2 would be equal to r times a sub k plus 1. Because this ratio up here will still hold for bigger values of k. So right here, I could write r times a sub k plus 1. But then I could continue on. So I'll just copy this down, r times a sub k. But then remember, what's a sub k plus 1? Well, that's just r, and that's another r. Let's try it like this. I like to color code this. It's kind of nice. And so I have this R here, and then this is another R times A sub K, because again, it satisfies that equality. And so then here, R times R is just R squared times A sub K. And so plus dot, dot, dot. Now you can kind of see what's going to happen. This pattern is going to continue on forever. So right here, what is this end part? This is just a geometric series. So basically what you have here is that you have a finite series up to this point because it stops there at A sub K minus 1, basically. And then you have a geometric series on the end. So if you take a finite series and add a geometric series to it, you can actually say when it's going to converge or diverge given the value of R. So whatever R is, it'll tell you when it converges or diverges. So when R is less than 1, we know the geometric series converges. So our series converges, and it converges absolutely because we are actually testing the absolute value of the sums of the sum of the absolute value of the terms. But I dropped off that absolute value. Again, it was just so you can see this idea. Like basically, we're testing to see if the series is a geometric series in the very end. And then if it's greater than 1, we know that it's going to diverge. So our series will diverge. And then if R is equal to 1, it turns out the test is actually inconclusive, right? So when R is equal to 1, there's a slight problem in trying to show that these two are, this is actually equal to each other. It's not quite equal to each other. Remember, because we are doing limits, so it's very close to, but not exact. So you're off there when it's equal to 1. But it's a nice little sort of heuristic proof to show you, oh, okay, so basically, what is this saying? This is saying, if you get out an R and it's less than 1, it's basically saying that you have the geometric series and it's going to converge. Whereas if you get R bigger than 1, was saying you have the geometric series and it's going to diverge because your R is bigger than 1. And then equal to 1, we're just kind of out of luck. It's that borderline case, which we don't get much information back about the actual series. Okay, let's look at the next test, because the next test is called the root test, and it's a great little test. It's not used as often as the ratio test in this class, but it's a nice test because it can speed up some of the harder problems that we've done with limits, really. So what does the root test say? So it says you have the sum of a sub n is a series, and then when you take the limit, all you have to look at is the limit of the nth root of the a sub nth, or the nth root of the absolute value of the nth term, basically. And it's equal to R, and then it's going to converge if R is less than 1, and it converges, we should write here, converges absolutely. And then when it's bigger than 1, it's going to diverge. And when it's equal to 1, it's going to be inconclusive. And to see why this one works, we'll do a couple problems in a minute. But to do this one, let's suppose this is a series. That's a little typo. So is a series. And the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to R. And so then what does that actually mean? So think about this. What this means is as n gets bigger and bigger and bigger, this thing gets closer and closer to R. And so in our ideal world, what this means is that this kth root of a sub k is equal to R for very big values of R, like 1 billion or bigger, right? So really, really big values of R, we can almost just say the kth root of a sub k is equal to R. And again, I put it in quotes because I am dropping off some absolute value stuff here just to make everything kind of nice and neat and easy to see. So we have our series right here. And so we just write it down, a sub 1 plus a sub 2 plus a sub 3 plus dot, dot, dot. And I go up to a sub k plus 1, a sub k plus 2, dot, dot, plus dot, dot, dot. Let's get rid of that equal sign there. And so then what does that equal to? Well, remember what each of these are actually equal to, right? Oh, I forgot to show that. So which means what? So now if you have this statement here, a sub k is what? Well, you just take the kth root, or the kth power on both sides. So raise this to the kth power on both sides, get rid of the kth root. And so you get a sub k equal to R to the k, which is great. So right here, you can replace that with r sub k. You can replace this with r to the k plus 1, and you replace this guy with r to the k plus 2, and so on and so forth. And so you get r to the k plus r to the k plus 1, and r to the k plus 2 plus dot, 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 which is equal to what? Well, you can just factor out the r to the k. So if you factor out an r to the k, what do you have left over? So we'll pull out this r to the k. And then what do you get left over? Well, what goes here times r to the k is r to the k. Well, that's just a 1. And then what goes here times r to the k gives you this r to the k plus 1. Well, that's an r. And I bet you can guess what comes next. R squared plus dot, dot, dot. And this, again, is just a geometric series. And so what we have, again, is basically a finite series here, right? Because it does end at a sub k there. So it's all the way up to a sub k minus 1. In fact, if you want, you can just put plus here. Let's do it in black so it pops. So right here, you can just put a plus, and there's an a sub k minus 1, basically, right here. So a sub k minus 1, and then plus, and then all this other stuff, which is a geometric series. And we know, therefore, if r is less than 1, this series, the geometries will converge. So this basically a sub n, so some of the a sub n's converge absolutely. If r is bigger than 1, we know the geometric series are going to diverge. So basically the series will diverge. And if r is equal to 1, it turns out the test is inconclusive. And that basically has to come up here with these quotes. It turns out we can't really follow through on this equality type of argument. In fact, if you actually show this, you actually do it with inequalities, right? So if you want to do it rigorously, you would do this with inequalities. And it's just a little bit, there's a little more detail that goes into it. But I think I like this type of proof for you guys because it's like you can see, you're just basically saying that if you take the nth root of the a-nth term, you get back a number all the time, basically. And then it's a geometric series in the end because you're basically adding up like 1 plus r squared plus r cubed plus r to the 4th at the very end, in essence, is what you're doing. So it's behaving like a geometric series in the end. So I can tell you if it's going to converge or diverge because of that. All right, so let's do some problems. So here are the problems we're going to do. There's 2 of them. You may ask the question, well, how do you know when to use the root test? Well, it always has to do with the fact that the root test involves a root, the nth root, basically. So if you have something to the nth power, boy, that nth root test is going to tear that thing apart, basically, right? It's going to be nice and easy. And then down here, it's a little bit trickier, but you do have an nth power, so it kind of lends itself like, hey, you might want to do a root test on this one. Although I'd probably do a ratio test on this one. So basically the rule is if you have a geometric thing or a factorial thing in your series, probably want to do a ratio test on it. Limit comparison turns out to be mostly like a p-series type stuff. So if you have something that looks kind of like a p-series but not quite, then that's kind of nice to do a limit comparison test on. All right, so let's see how this works. So let's come over here and let's try this problem. And I forgot to write down the root test for you. So what do we want to do? Let's come back here and I can snip it, I guess. So let me snip it here. So we can carry that along with us if we want to. So new, let's snip this so we can carry it with us and we'll get the absolute part. And we'll come over here and we'll lay it down right there. All right, and we'll make it kind of small because we don't want that big. All right, so we'll put it over here. So we have it over there. And then we'll do it on the next one too. So the next one's right here. So let's put it over here. So we have it. I grabbed the wrong thing. Okay, so I'll just throw that over on the side here. So you have it up. Now remember, you won't have these tests written down when we take the exam, so you're gonna have to remember them somehow. I always recommend flashcards. It's the easiest way. So how are we gonna do this? So the idea is what? Well, here's my nth term right here. So if you want, you can identify your term. A sub n equals 2n squared minus 3 divided by 2 n squared plus 4. That's all to the nth power. And so I'm going to take a look at the limit as n goes to infinity of the nth root of a sub n. I always write this down. That helps me remember what the test is, actually, if I write it down every single time. And I have to put the absolute value on there, so don't forget that, because that's actually important. Because this is really a test for absolute convergence, but that implies regular convergence. So limit as n goes to infinity of the nth root of, we slap the absolute value of 2n squared minus 3 divided by 7n squared plus 4. And that's all to the nth power. And again, it's absolute value. And so then this is going to be equal to, now we can drop off the absolute value because everything's positive, basically. And then what's the nth root to the nth power? The nth root and the power n are going to cancel, basically. So it's going to be a limit as n goes to infinity of 2n squared minus 3 over 7n squared plus 4. And you know what that limit is. If you want to show a little bit of work, what we can do is we can cross off the lower degree terms on top and bottom and just write the limit as n goes to infinity of 2n squared over 7n squared. And if you want to just say equal to 2/7 right now, you can, but I'll just do all the little steps. That's equal to the limit as n goes to infinity. So again, you can cross off these terms because that's just a little bit of algebra, right? So then 2 over 7, and of course the limit, sorry, of a constant is always a constant. So 2/7, which then I want to make my statement. This is less than 1. So therefore, my series, let's give it a name, S. So therefore, S converges by the what? Turn off my alarm here, guys. Sorry. So by the root test, right? So by the root test. All right, and so that's how you use the root test here. And we have one last one to do. So that one wasn't too bad. So maybe this one will be a little bit trickier. That's what I'm thinking. So over here, here's my term. So let's write down my term. A sub n is equal to 2 to the n over n to the 10th. And I want to find what is the limit as n goes to infinity of the nth root of the absolute value of a sub n. And so it'll be equal to the limit as n goes to infinity. I take the nth root of, and I have 2 to the n over n to the 10th. If you want, you can just drop off the absolute value because everything is positive here. So this is going to be equal to the limit of the, as n goes to infinity, of the nth root of 2 to the n over n to the 10th. And now, when I deal with the nth root, sometimes it's nice to keep it as a radical, but you could also write it as a power. And so I'm going to write this as a power, so the limit as n goes to infinity of 2 to the n divided by n to the 10th. I'm going to raise that to the 1 over n. So that is the nth root. So that's equivalent. When you raise something to 1 over n, the same as taking the nth root of it. One, you're using radical notation, the other using power notation. But when you use this power notation, it's kind of nice because basically what? You could just multiply the exponent. So we multiply these exponents together and we get the limit as n goes to infinity. And on top, if you take n times 1 over n, you just get 1. And on bottom, I have n to the 10 over n. And so this will be equal to, now you just got to figure out what the limit is as n goes to infinity on that bottom piece. And so now to do that, that's a little bit tricky. All right, so you have two choices. You can work with inside the problem, or we can start a new problem below it. I guess we can stick with it. So this is the same as 2 divided by the limit as n goes to infinity of n to the 10 over n. And then hopefully you guys notice if you plug in infinity here, what happens is you're going to get 1 to the infinity on that bottom down there. So you have 2 divided by on the bottom. When you plug in infinity, you get infinity for n, and then 10 over infinity is 0. And so that's one of those exponential indeterminate forms. So we're going to have to bust out some e's and ln's here to solve this problem. So it's going to be equal to, so let's do this. So we're going to have 2 divided by, and then we have the limit on the bottom as n goes to infinity. And I'm going to rewrite this as e to the ln of. So e to the ln of n to the 10 over n. And then that 10 over n can now come down in front here. And so it'll be equal to 2 divided by the limit as n goes to infinity of e to the 10 over n, and then all times ln of n. Which is pretty nice because now if you plug in infinity, what happens? You get 2 divided by, and I'll have e to the, and then 10 over infinity is like 0, and then times ln of infinity is like infinity, which is pretty nice. In fact, actually, I like this even better, so I think I'm going to do this. If I just draw the line over right here, now I have infinity on top and infinity on the bottom, which is L'Hopital type. That's even better, right? So I'll just rewrite it like this, 10 times ln of n divided by n, which is the same thing I had before, just written in a different way. But now I can easily use my L'Hopital on this guy. And so this is going to be equal to the 2 on top divided by the limit as n goes to infinity of e to the, and then I'll take the derivative on top here. And so what's the derivative of 10 times ln of n? Well, that's 10 times 1 over n. And then divided by, what's the derivative of n? Well, that's just 1. And so that's just equal to 2 divided by the limit as n goes to infinity of e to the 10 over n right there. And that 10 over n is in the exponent. So now let's let n be infinity and see what we get. So we get 2 divided by e to the 10 divided by infinity. If you want, you can put that into quotes. Although, what's 10 divided by infinity? It's like 0. So it's like 2 divided by e to the 0. And e to the 0 is 1. So it's like 2 over 1, which is 2. Got it. So this whole limit right here, what do we get back? We get back the number 2, which is bigger than 1. So therefore, what? Therefore, our series S, therefore S diverges by, not the ratio test, but by the root. Right, so by the root test. Here we go. And so that's a nice little root test problem. And you could kind of see why it's going to diverge. It's like 2 to the n is much stronger than n to the 10th. It's just it's going to dominate in the end there. But it's a nice little problem involving limits. All right, guys, that's all I have for you today.